Welcome back to The Explainer. Today, we're popping the hood on the engine that drives pretty much all of modern AI, the artificial neural network. From the AI in your favorite games to the systems predicting the stock market, ANNs are the powerhouses, and we're going to break down exactly how they work.
Okay, so to really get why neural networks are such a big deal, you first have to understand the massive problem they were designed to solve. And trust me, it's a huge one. It's a problem of memory and, well, infinite possibilities. I mean, just think about a complex video game for a second. Every single combination of pixels on the screen, every possible place an enemy could be, every single choice you, the player, could make, the number of possible situations or states it's practically endless. How could any system possibly prepare for all of that?
Now, for a simple game, right, like tic-tac-toe, an AI could basically have a giant cheat sheet. It's called a Q table. And for every possible board state, it just looks up the best move. Easy. But for a complex game like Atari, forget about it. That cheat sheet would need more entries than there are atoms in the known universe. It's just not physically possible.
So if memorizing everything is completely off the table, how does an AI ever learn? Well, it needs a shortcut, a really smart one. And that is exactly where the artificial neural network comes in. It's a total game changer because it doesn't try to memorize, it generalizes.
So instead of trying to build that impossibly huge cheat sheet, the ANN works more like a flexible formula. The technical term for this is function approximation. You feed it the situation, and it calculates a probable best move. It's making a smart guess, not just looking up a pre-written answer.
And this right here is the critical point. An ANN does not need to have seen every single situation before, not even close. It learns the underlying patterns from the data it has seen and then uses those patterns to make really solid, educated guesses about brand new situations it's never encountered. It learns the rules of the game, not just the answers to the test. And here's something kind of cool. If you look at this table, you'll see that neural networks didn't just appear out of nowhere. Their roots are actually in simpler statistics. You can think of an ANN as a super-powered version of a model like logistic regression. The core ideas are really similar. We've just scaled them up and given them new names. What used to be called coefficients are now weights, and so on.
But how does a network actually get powerful enough to solve these really complex problems? Well, the secret isn't just in the individual components, but in how they're arranged. The real magic is in the structure. Let's try an analogy. Imagine you're trying to separate two groups of dots on a screen, blue dots and red dots. If all the blue dots are on the left and all the red dots are on the right, well, that's an easy problem. A single straight line is all you need to draw a boundary between them. That's what a very simple network can do. Okay, but now picture those same dots all mixed up. You know, a big swirl of red and blue all intertwined. Now that single straight line, it's completely useless. It can't possibly capture the complex relationship between all those points. And that's the core challenge, right? We know a simple line won't work, so how do we give the network the ability to draw a more sophisticated, more flexible boundary that can actually snake its way through that messy data and find the real pattern? And here it is, the brilliant solution. You add hidden layers. Think of it like this. Each little node in these hidden layers can only draw its own simple, straight line. But when you get a whole bunch of them working together, their simple lines combine to create one super complex, curvy, and incredibly accurate boundary. It's like teamwork for lines. But you gotta be careful. Getting this structure right is a really delicate balancing act. If you have too few hidden nodes, the model underfits. It's just too simple to see the pattern. But if you have too many, it overfits. It basically just memorizes the training data perfectly, but then it completely fails when it sees anything new. The goal is to find that sweet spot, right there in the middle. Okay, so we've got the structure, we understand the hidden layers, but how does the network actually learn? Well, it all comes down to finding the perfect strength or weight for every single connection between all those nodes. The whole learning process is a constant loop. You can think of it as guess, check, and correct. It starts out with totally random connections, so its first guess is terrible. Then, it checks how wrong that guess was by comparing it to the right answer. And then, and this is the genius part, it works backward to figure out which connections were most to blame for the error. Finally, it just nudges those connections in the right direction and starts the whole cycle over again. That fourth step, working backward, that's the magic ingredient.
It's called backpropagation. It's this elegant algorithm that lets the network assign blame for its mistakes. It figures out exactly which weights to tweak and by how much, all the way back through the entire network, to make its next guess just a little bit better. And this isn't a one-and-done deal. The network runs through this entire learning cycle, this epoch, over and over and over again, thousands, sometimes millions of times. With each pass, the weights get a tiny bit better, and the network's predictions get just a little more accurate. So, after all of that, after thousands of these learning cycles, with the network constantly guessing and checking and correcting itself, what's the end result? What's the core idea you should really take away from all this? When you boil it all down, it comes to this. For really complex problems, you just can't memorize every possibility. It's impossible. So neural networks give us a way out by approximating answers instead of storing them. And they learn how to do this by repeatedly guessing, calculating how wrong that guess was, and then using that magic of backpropagation to adjust themselves to be better next time. And that leaves us with a pretty fascinating final thought to chew on. If the core of modern AI is built not on certainty, but on incredibly sophisticated guesswork, what does it truly mean for a machine to know anything at all? Thanks for joining me on this explainer.